Hello, this is Mike and welcome to BitFixer. Today we have the new board for the ROMulator Z80. We've added some additional signals that were necessary, including the M1 and memory request and I/O request. And if you're new to the project, the ROMulator is a RAM and ROM replacement device for 8-bit CPUs, which also includes the ability to debug a running machine by halting the CPU and reading out the contents of memory or replacing memory, including the ROMulator 6502, which works with 6502 machines like Commodore PET, Apple II, VIC-20, etc. And this one will now support Z80 machines like this Timex Sinclair 1000, ZX Spectrum, and TRS-80 models, and many, many more. So let's go ahead and build this up and let's test this out on this Timex Sinclair 1000 and another machine which I will show you later on. And while we assemble the ROMulator Z80, I wanted to say thank you to PCBWay for sponsoring this episode. PCBWay is a service which offers printed circuit board manufacturing and assembly, along with several other things like CNC machining, 3D printing, sheet metal fabrication, and injection molding. And new members get a $5 welcome bonus which can be used on your first order. Thank you to PCBWay. So we'll start out with the Timex Sinclair 1000 and programming the ROMulator to bypass the entire memory map just to prove that there are no obvious flaws in the board design. Alright, the ROMulator is plugged in, it's programmed with the bypass firmware, and the video is hooked up, so let's give it a try. Alright, great. So we have the K here. So the bypass is working. This is the new board. So let's go ahead and try that 2-byte replacement that we did before, and I just want to make sure that that still works. Okay, I've added those 2 bytes. It should be enabled for both read and write on address 18432 and 18433. So, okay, good. We still have the K. Alright, I think it is a comma indeed. I found the comma. Okay, let's try 1, 2, 3. Okay, good. Okay, 123, great. Can you even see that? I guess not. Sorry. Here's 123. Poke. Oops. I'm not good with this keyboard here. 18433. Let's try another value. Let's do 23. Why not? Okay, so that looks good. And now we print 23. Okay, great. So we've replaced the 2 bytes. You can read and write to them, which is great. So looks like we do not have any major hardware regressions on the board. So let's go ahead and try this on another Z80 machine. Before we go on, I just wanted to say a quick thank you to everyone who left very informative comments on the architecture on the Timex Sinclair 1000 / ZX81. I definitely learned a lot about how this machine works, and a lot of interesting tricks to make this computer work with a very low amount of memory. I also agree that probably for a very preliminary test of the ROMulator Z80, this is probably not the easiest choice for a very first test. So I will definitely revisit this in the future, and it'll probably need some form of special handling to get all the features to work. But for now, on with the next test. We're going to go back in time a bit to what I believe to be the first commercially available Z80 computer. This is a Z80 system from the Digitalgroup, and this was released shortly after the Z80 itself was released in summer of '76. It happens to have a fairly simple architecture. There's a 256-byte ROM at the bottom of memory space. The rest of the memory space can be entirely filled with RAM, and keyboard, TV out, and cassette reading are handled by reads and writes to I/O ports. If you're interested in hearing more about this computer, check out one of my 2 videos on the Digitalgroup in the description. For the first test, we're going to try pretty much the same thing as we tried last time, except now we have some new signals added. We have M1 coming in, memory request, IO request, and similar to before, first test, I'm going to disable everything. We still have the RAM present in the FPGA, but I am disabling it for every address. So what we should see is basically just going to run as normal. So inside the large chassis of the digital group computer, we've got 5 cards total. These two are memory cards. I believe one is a 32K and one of them is an 8K. A CPU card with the Z80, which you'll see in a little better detail in a second. And these two, I'm not sure which is which actually. One of them is, I think this one is for the keyboard, an IO card to drive the IO port and therefore the keyboard. And the other one is for the cassette and TV display. So what we're going to do is we're going to take the CPU card, and I'm just going to try it once with a newer Z80 just to make sure that there's nothing odd going on, because I want to preserve that nice ceramic Z80 in here. So we'll do that, and then we will eventually take these memory cards out, program the ROMulator to replace RAM where those cards would sit in memory space, and we'll see if that works. Got it all connected up. Just do a quick power up as is to verify that it's still working. And it is. There you go, you can see the digital group when it starts up. Gives you the message read Z80 initialize cassette. This one is the cassette version. This also came with a disk drive unit. You need a separate ROM for that, but this one reads from cassette, so it is working as expected. So here's a closer view of the digital group Z80 CPU board. I've replaced the original white ceramic Z80, which is here. Its own protective little baggie, and put a newer Z80B CPU in here. I just want to make sure that it works the same. And here's the ROM here, which we'll eventually be replacing, hopefully. And let's see if this works the same as it did before. Okay, power up number 2, CPU board back in with the newer Z80. Let's just make sure that it's still running. And yes, it is. Great. And just realized we should do one more test with the memory cards out. There is actually, I think, 2K of RAM on the CPU card, so it should work without the other memory cards in there. Just wanted to verify that because actually we have a physical limitation here. This card is too close to the Z80 CPU here, so it would actually block it if we put the ROMulator in there. So let's find out if it works without the RAM cards in it first. And it should. Okay. Oh, I guess not. I guess it needs at least some of that RAM in there. Let's try that again. I replaced what I believe to be the 8K RAM card, which I think is the RAM that you need to start up. Maybe wrong. Let's wait for it to warm up here. And go. Okay, good. Yeah, so 8K RAM card is back in. That appears to be all we need to start up, at least this far. So now I think we are ready to try the bypass version of the ROMulator Z80 in here. Okay, this is the first real test here. ROMulator Z80 is in place on the CPU board. And let's plug it in and give it a try. Who knows what will happen. Alright, let's wait for that to warm up. And here we go. Alright, there you go. Still have the message. ROMulator is getting power. That's good. And we're just bypassing the entire memory map right now, and we still get the Z80 initialize cassette message. So that means that it's nothing inherently wrong with the board design as far as I know. And I think next thing we will do is let's go ahead and run a memory test on here, which should show us the 8K plus the 2K that we have on the CPU card, and then we'll try to add some memory to it, and then we should see that result change. I have a memory test program in audio format here, which I will attempt to load through the cassette port on the digital group. Let's go ahead and do that. So start up, read Z80 and select cassette, so I'll play, and let's just see if this works. Alright, it is loading now. Interesting way. Okay, I got memory tests up here, and oops, well I just forgot that I don't have the keyboard connected. And actually the original keyboard I have for this one does not currently work. It's one of those foam and foil capacitive keyboards that always goes bad. I haven't restored it yet, so I have a different solution for that, which I will show you right now. So the keyboard solution for now is this little project I had from several years ago. It's a microcontroller hooked up to the keyboard port on the back of the digital group here, and this is it takes a serial input through a USB to serial connector and translates it to parallel ASCII, which is what this keyboard wants. So we should be able to run the memory test now. So let's go ahead and do that. Got it queued up here. Alright, start up. Alright, we have memory extent test, memory data test, memory speed test. So let's try memory extent test. Oops, I'm not in the right window here. Okay, 1, there we go. So the memory extent test, we see RAM found on system 100000 to 107377. Now, these addresses are in octal, so I'll convert those to see what that translates to. And then we have 0 to 037377, end of test. So I just did a little review to remember how octal counting works in the computer world. It's base 8 mathematics, but unlike hexadecimal, where every digit has the same number of bits, in octal you're actually counting these groups of 3. So these group of 3 digits is equivalent to 2 hexadecimal digits, and essentially have this one is worth 3 bits, this one is 3 bits, and this one is 2 bits, and so on. So it's in groups of 3. That's a little different. If you're just doing strict base 8, every digit would be 3 bits, or equivalent to 0 through 7. Anyway, just if you're converting 107377, you go up in the powers of 8. So 1s, 8s, 64s, and you add these up. The highest number you can have here is 377, and that's 255. So the lower position is 255 times 1, and then up here 107. So again, you do 1s, 8s, and 64s. So this is 64 plus 7, and that's 71. And then the ones in this position you multiply by 256. The same as you would do with hex. So 71 times 256 plus 255. So we basically get up here, and then this is 18K. Yeah, so we have the ranges that we saw on the memory test. 1, 0. I'm missing a 0 here, but we basically see 16K to 18K and 0K to 8K, and that actually matches up with what we would expect. We have an 8K memory card that's mapped to the lower 8K of memory, lower 8K addresses of memory, and then that 2K that's on the processor card, I double checked with the documentation, and that is jumpered to be between 16K to 18K, so that makes sense that they have 2 different regions there, as shown in the memory test. So what we saw before from that memory test is we already have addresses 0 to 8K populated, and we have address 16K to 18K populated. So what I'm trying to do is I've created this chip select signal for the RAM where address is greater than or equal to hex 2000, which is 8K, and address less than hex 4000, 16K. And one of these 2 signals is active, which is why they're not, because those are low active. So this should select the RAM when we are doing a read or write operation between 8K and 16K and therefore replace that whole section. So I will build this, program the ROMulator, and we'll give it a try. Alright, we have that programmed up, and we'll try that memory extent test one more time and see if we see any difference. Alright, memory extent test, here we go. Okay, what's going on? Do I still have my... There we go. Okay, look at that. RAM found on system. Yeah, definitely different. 0 to 107, 377. So I still have to do the math to figure that out. Alright, well it looks like that last test was successful. We replaced 8K to 16K. And now I'm going to go all the way from replacing everything from, this is 256. This is right above the ROM on the CPU card, and then all the way to FFFF. So this should give us a full 64K of memory, with the exception of the lowest 256 bytes, which is ROM, and we will test that later, but first I want to see if we can just fill up the whole memory map now. Alright, next attempt. This is replacing the full memory map except for the bottom 256 bytes of memory. Oops, okay. That's not good. Alright, let's try that again. I did a few other tests replacing different regions of RAM and eventually found that I could replace all the way down to right above the ROM address, and I could go up to at least 32K. But if I went too high in memory space, then the machine would fail to boot. So that was kind of interesting. Okay, so now we are back to what we originally tried that didn't work before the ROMulator was in here. There are no memory cards. The only memory in the system is this 2K that is currently mapped to between 16K and 18K in the memory map. And that is already being replaced. So let's turn it on and see if it's really working here. Alright, look at that. So no memory card in the machine, and the Z80 ROM, or the cassette ROM I should say, is still loading up properly. But I believe that means that we are successfully replacing RAM in this computer. So at this point I'm pretty confident that we're replacing RAM properly for the digital group on the ROMulator. I'm not 100% sure why we're not able to go all the way up through FFFF on the memory map yet, but I'll put that aside for now. And I think next is time to try to replace the ROM in the ROMulator as well. So this is the ROM here. It's a 256 byte ROM. So first step to get that working is we have to get the contents of the ROM. I don't happen to have a ROM reader on hand, but can always try to throw one together with a microcontroller or something. But in this case, there is no need, because in the documentation for the Z80 operating system, the entire ROM contents are listed here. That's one of the nice things about computers from this sort of hobbyist era in the 70s. They just have all this stuff right here. It's open source before that was even a term. So I've actually done this for another project a while back for a digital group emulator, which I talk about in one of those other digital group videos. But I'll just grab the source code that I have and make the ROM image, and we'll try to replace the ROM on here as well and see how that works. I imported all the code from the 6502 version of the ROMulator over, and I attempted to make the minimum required changes in order to adapt the signals on the Z80 to fit what we were expecting for the 6502. And let's just look for a second about the difference in the signaling when a memory access happens on these two processors. On the 6502, the important signals are the address bus, 16-bit address bus. There's this read-write bar signal, which is logic high when you're reading, logic low when you're writing, and then this signal phi2, or phi2, I don't know, however you want to say it, I'm going to say phi2. Phi2 out, which is a clock signal that's derived from the input clock signal you give it, and that is logic high when the operation is active. So between those three things together, you know when to enable your memory in order to support a read or a write. On Z80 it's a little bit different. address bus is the same, but now you have a separate read and write signal. Both of these are active low, so it goes low when there's a write here, it goes low when there's a read. In addition to that, you also have this memory request, I/O request, and similarly those go low when those operations are active. That happens at the same time as write and read. So these are in addition to write and read. You have more information. Also there's M1, which is a special case when you are reading program code as opposed to the data. So if you have like a read operation, when the CPU is fetching its instruction, this is going to go low, but when it's just reading data, it's not going to go low. So as far as I can tell, the minimum change we need is to adapt to what we have already, we need something that's equivalent to the read-write signal, and we need something that's equivalent to the phi2 out signal from the Z80. So read-write bar here, we need something low when it's writing and high when it's reading. This is essentially the same as the write signal, so that we can just directly use the write signal instead. We will have to use the memory request later, but for now we're just trying it as simply as possible. And the phi2 signal, we need something that will go logic high when there's an active operation, and that can be achieved by taking write and read together. We basically invert write and read, and then we AND them together. So when either of these is active, then we have this equivalent signal is going to be logic high. So that's what I did at first. So the first run through with the ROM replaced, we got a garbage screen here, which means something wasn't working. And after some digging around, I realized that I had my wait signal backwards, which means that the Z80 was trying to start before the ROMulator had a chance to load in its full RAM contents. And I got that fixed and tried again. And that still works. It appears to work. Let's try changing some characters here just to verify that we're really reading off of that and not off of the original ROM. I'm looking at the ROM listing for the Z80 cassette ROM here, and you can see the text at the beginning, read Z80 initialized cassette, but looking at a hex editor, it's not visible as ASCII text, so I think that possibly one of the bits, maybe the high bit, is on when it shouldn't be on. I'll double check there, but I'm just going to change a few bytes in here so we confirm that we have changed the ROM. Alright, I changed that string in the ROM, and let's boot it up, and this will prove whether we've actually replaced the ROM or not. And there we go. Instead of initialized, it says read Z80 ROMulator cassette. So we have successfully replaced the ROM at address 0, the 256 byte ROM. And now it looks like, yeah, we have both RAM and ROM replacement working, and it's building in the same way as the 6502 version. And you can specify the ROM and RAM ranges in those config files. We're very close now to having this work as we expect. We have RAM is being replaced successfully, ROM is being replaced successfully. One thing that you did notice is, and kind of expected, is that because we're not yet using the memory request line in the enable for the onboard RAM on the ROMulator, there's no way to distinguish between accesses to I/O and accesses to memory in the lower addresses. The 256 I/O ports at the bottom of memory space. So what that means is that right now when you boot up, the keyboard doesn't work and you can't load from cassette. So to fix that, we incorporated the memory request signal into the enable logic here. And what that means is that whenever the memory is not being requested, therefore I/O, we should revert back to enabling the chip select for the main board. So we should pass through anything that's an I/O request. And when we try that, there's kind of an interesting effect here. You see it starts off smoothly, but then instead of just loading bytes across the screen continuously, it stopped and slowed down. So there's something not quite right with the way that's loading from cassette, and that's going to be yeah, see, and it just stops, it won't load entirely. So there's something wrong with the IO read request. Well, after spending time looking at this and going back in the history and finding when it broke, turns out that the problem was this ready line, which is actually the wait signal in the Z80. I was only using our own wait signal that we generate while we're reading memory map into RAM, but it turns out there's also an input ready or wait signal coming from the main board as well, and that's what the cassette interface is using to slow down the CPU during a program load in order to give it the proper data on the data bus. And since we weren't doing that, the CPU is running too fast and we weren't loading properly. So let's give that a shot again. It should be fixed and we should be able to load from the cassette again without incident. And there you go, that's the way it should look. So great, that's the IO and memory are disambiguated now, and the wait signal is combined with the wait signal that we generate. So it looks like everything is working now. We have RAM replaced, we have ROM replaced, and we're able to have IO working as well. And then one last thing, finally figured out why we were previously not able to replace all the way up to FFFF on the memory map. Turns out that when you have an IO request active on the Z80, well, you're actually only guaranteed to have the bottom 8 address lines contain valid data. So, at least according to the Z80 manual I was looking at. But what that means is that since we weren't using that memory request line before to separate IO and memory, then it was definitely possible that there would have been an IO request for, you know, port 0 or port 1, but it had some other value in the top of address space, and that was you know, basically it was sending garbage to the CPU and therefore it wouldn't boot. So yeah, so I just started it up with everything replaced, and now interestingly you see the RAM found on system is 0 to 0, which just means that every single value, it looped all the way around and every single address was valid. So now we have a full 64K memory map, and yeah, I think that it's more or less working now. Well, I think I'm going to end it there. We still have more to talk about as far as the debug functioning and reading and writing memory maps from a halted CPU, but I'm going to leave that for another time. The video is already getting a little bit long as it is. So what's next? Does this mean that the ROMulator Z80 is completely finished? Well, there is one more thing that I had some concern about, and that is the support for DMA on the Z80 CPU. And DMA, or direct memory access, means that the CPU and another device in the system can share memory via the same address bus and data bus. And when you request DMA, then the CPU will allow the other device to directly access memory. And that is currently not supported on at least this iteration of the board for the ROMulator Z80. And in order to do that, it is possible. I will have to probably steal a couple of other I/O pins on the FPGA that are currently used for other things, because we're completely out of I/O pins on this part. But let me know what you think. I would like to know if there's a good way to test that DMA function on existing Z80 computers. I'm not aware of how prevalent the use of DMA was. I know one use is front panel for older systems, and using a front panel to directly enter in data. But I'm curious about what other devices might have used that. Probably some sort of storage devices, disk drives. Anyway, let me know what you think. If DMA support is a critical thing in the ROMulator Z80, and yeah, just leave me a comment. Anyway, thank you very much for watching, and see you next time.